1 second. Okay, so welcome everybody. Today I'm happy to introduce Sai Bi in our talk at Tübingen seminar series. Sai is a PhD candidate at the Department of Computer Science and Engineering at UC San Diego, advised by Ravi Ramamurthy. Before coming to UCSD, he obtained his Bachelor of Engineering in Computer Science from the University of Hong Kong. Recently, he has done some really nice work in the area of learning-based appearance and geometry acquisition. So, Sai, we are looking very much forward to your talk.
Okay, thank you. Thank you for introduction, Andres. So let's get started. So hello, everyone. Thanks for coming to this talk. So today I'm going to present our research on reproducing the appearance of real-world objects and scenes to create digital 3D content. So nowadays, it is estimated that we people take about 1.7 trillion photos a year. Photos have become the dominant way for us to share memories and life experiences. That's why now we have 1 billion active users on Instagram every month, and more than 95 million photos are uploaded every day. However, photos are not a perfect media for preserving our memories and sharing experiences. I still remember the day when I visited the Sagrada Familia in Barcelona. I was fascinated with its magnificent structures and spectacular lightings. However, when we look back at that day, instead of looking at the picture as a bystander, I would prefer to be part of the scene, fully immerse myself into the scene and enjoy the beautiful sunlight. A single photo cannot allow us to do this. We need to have a full 3D representation for the great architecture. However, it remains very challenging for us to create digital 3D content. Usually, super complex tools and special expertise are required to finish this task. Compared to the 1.7 trillion photos, we may think about how many 3D models we make every year. And for most people, the number might be 0. In contrast, one easy way to create the 3D content is to scan abundant real-world objects and scenes and directly reconstruct a full 3D representation from the scans. My research aims to develop efficient and accurate methods to acquire the appearance of real-world objects and scenes. Acquiring the appearance of real-world objects and scenes has been a long-standing problem in computer graphics and computer vision. It has abundant applications in many fields, such as video games, cultural heritage preservation, virtual reality, and augmented reality. To acquire the appearance of object, one traditional method is to first reconstruct the geometry of the object, usually represented with a triangle mesh. And then we recover its material properties, usually represented by its BRDFs. These 2 components allow us to visualize the object under novel lighting conditions from an arbitrary viewpoint. Another approach for this task gets rid of the complexity of reconstructing the geometry and the materials. Instead, it captures the object from multiple viewpoints and multiple lighting conditions, so that we can directly query how the object looks like given a novel viewpoint and lighting. My research develops the methods on both categories. We develop different representations for single appearance to meet different functionalities. In our paper in SIGGRAPH 2017, we propose an optimization-based method to recover accurate texture maps for RGB-D reconstructions. In later work, we propose a learning-based method to synthesize photorealistic images at no viewpoints from a sparse set of 6 images. We further extended this work and recovered the full geometry and BRDF from only 6 images captured using captured under collocated camera light. Our method supports both no viewpoints and no lighting conditions. In addition to mesh representations, our latest work presented in this year's ECCV learns a volumetric representation for the scene. Our volumetric representation supports free viewpoint relighting. In this talk, we will cover 3 of them. Let's look at the texture mapping first. With the available of consumer depth cameras, nowadays we can easily scan a scene and produce its geometry using techniques like kinetic fusion. However, only having geometry is not enough. We also need to reproduce high quality appearance. From the color stream, we can get a set of images taken from different viewpoints. Given these images, ideally we can project them onto the geometry and blend them to produce a nice texture map. However, in practice, due to the existence of inaccurate geometry and camera poses, as well as optical distortion, naively projecting and combining the misaligned input images produces blurring and ghosting artifacts, just as the video shows. Previous works tackled this problem with two different kinds of approaches. Instead of blending the projected images, some approach try to solve this problem by selecting only one view for each face. However, these approaches are not able to handle large inaccuracies in challenging cases and produce visible seams in the final texture map. Another solution for this problem is to align images from different viewpoints. For example, I might address the misalignments between images by aligning the projected images to a reference view with optical flow. The recent work of George of the optimization system to find the optimal camera poses, as well as non-rigid corrections of the input images. They use local warping to do non-rigid correction, and it is not able to correct large inaccuracies and produce the ghosting and blurry artifacts. In this work, instead of projecting and blending the original image, which are misaligned with respect to kind of geometry and camera poses, we propose a novel global patch-based optimization system to synthesize an aligned image for every input image. The synthesized image has most of the information of the original image and are similar to them, but it is aligned with each other as a result of our global patch-based optimization system. Given these aligned images, we can safely project them onto the geometry and do a simple blending to get a high-quality texture map. Compared to optical flow or local image warping, our patch-based image synthesis can better handle large misalignments between images. Let's look at this problem again by studying a simple case. Here, we have a rough geometry and two input images. We illustrate the texture mapping process from a novel viewpoint. First, we project one image to a novel view and get the projections. Then we project the other image to the novel view. Due to the inaccuracies in the geometry, camera poses, and optical distortions, these two projected source images are typically misaligned. For example, the insets show that the positions of our characters AR and GR in the two projected source images are different. Therefore, combining these projected source images produce a texture map with blurring and ghosting artifacts. To solve this misalignment, we aim to synthesize two aligned images for the input image at the two input views, which we call target images. To reconstruct each target image, we keep the overall view appearance of the source image, but move its content to correct the misalignments. In this case, if we project these target images onto the geometry, these two images will be aligned. Note the difference in positions of these characters AR and GR in the source and target images. In this case, since the projected images are aligned, we are able to produce a ghost-free high-quality texture map by simply blending them. Our main observation is that to produce a high-quality texture map, the target images should have two properties. First, the target image should be similar to the corresponding source image. Secondly, the projected target images should be consistent. We propose a global energy function to codify these two properties. Now let's look at the first property. To satisfy first property, we need to ensure that the target target images should contain most information from its source image in a very coherent way. Here, the coherence means that there's no new structures or artifacts in the target image. We use bidirectional similarity to meet this requirement, which consists of two terms, including completeness and coherence. Let's look at the completeness first. Given a source image and a target image, the completeness term measures how much information from the source is included in the target. Given a patch in the source image, we find its most similar patch in the target image. We define the completeness term as the distance between these two patches. This is done for all patches in the source images. From this, we can see that by minimizing this term, we are ensuring that each patch in the source image will have a similar patch in the target, thus enforcing that most information in the source image is contained in the target image. Similarly, for the coherence term, we are trying to avoid any new view structures or artifacts in the target image. For each patch in the target, we find its most similar patch in the source and define the coherence as the distance between them. This is done for all patches in target. By minimizing this term, we are ensuring that most patches in the target come from the source image. That is, no new structures or artifacts. Therefore, by combining these two terms, we can satisfy the first property of the target image. That is, target images should contain most information from its source image in a very coherent way. We have just talked about the first term of our patch-based energy function, that is the similarity term. It ensures the target images contain most of the information from the corresponding image in a very coherent way. We still need to satisfy the second property. That is, the projected target images should be photometrically consistent with each other. Now, let's see the energy function for the consistency term. Just as the figure shows, given the geometry as well as two target images, the high-level idea is that for the current target image, we project the other target images to the current view. And then we ensure the consistency by minimizing the L2 difference between the current image and the projected target image. Let's see this part in more details. For a pixel on the current image and its color, for the pixel on the current image and its color, we find a corresponding pixel on the other image, on the other target image that will be projected to this pixel. To ensure consistency, we enforce these two colors to be the same by minimizing their L2 difference. This is done for all target images and for all pixels on the current image. Also, we assign each term different weights. It basically gives smaller weight to the cameras that look at the surface at a great angle and that are far away from the object. For the sake of alternative optimization, we introduce a new variable which stands for the optimal target images at each view. By minimizing this term, we could ensure that all target images are consistent with each other. In summary, our patch-based energy function is as following. The first term is the consistency term. The first term is the similarity term. It measures the similarity between source images and target images. And the second term is the consistency term, which measures the difference between target images. The final energy function is the weighted average of these two terms. Our approach synthesizes aligned images by optimizing a global patch-based energy function. We propose to optimize this energy function with a two-step approach. The first step is the alignment. During alignment, patch search and vote is performed between the source and the current target images to obtain new targets. For initialization, we set the target image same as the source image. Note that where the source and target images are similar, the target images is reconstructed by moving the source content to ensure alignment. The second stage is reconstruction. In the reconstruction stage, the synthesized images are projected onto the geometry and combined to produce texture images at different views. And the textures at each view are used as the new texture images at the alignment stage in the next iteration. In case the synthesized images are misaligned, which is usually the case at the beginning of the optimization, this process produces textures with ghosting and blurring artifacts. The next iterations of the alignment process will then try to reduce the misalignment between the targets, which consequently results in a texture map with fewer artifacts after reconstruction. We continue this process of alignment and reconstruction iteratively until convergence. We apply a multi-scale optimization to make the optimization process more robust. This video shows our optimization process for a single view. Please pay attention to regions indicated by the red box. We can see that the patch matching is gradually modifying the structures of the image so as to align them. As you can see that the characters W here, you can see that the optimization process gradually changes the structure of the character so as to align it with other views. Let's see it again. So this video shows the comparison between single view selection method and our method. Single view selection selects one view per face by solving an optimization system to hide the seams between adjacent faces. However, their method is not able to produce satisfactory results in this case, since they assign consistent textures to some of the adjacent faces and produce visible seams and tearing artifacts. The local warping method also fails to correct a significant misalignment in this case. Therefore, their results suffer from ghosting and blurring artifacts. In comparison, our method synthesizes aligned images and is able to produce high-quality texture maps with no obvious artifacts. Let's examine the toising. It has complex and inaccurate geometry. Single view selection method produces tearing artifacts and visible seams around the pillar. Local warping method also cannot correct the large misalignments and generates blurring textures. Finally, this scene is particularly challenging for all the methods since the subject was in slight motion during the capture process. In this case, the single view selection method produced visible seams due to incorrect labeling at the adjacent faces. This method does not have the flexibility to correct these misalignments and produces blurry textures. While this approach produces results with artifacts, our method properly handles all the inaccuracies and generates a high-quality texture. That's all for the texture mapping. While a high-quality texture can reproduce the color of the object, it does not allow us to visualize the object under normal lighting conditions. Therefore, in later work, we propose a method to learn relightable reconstructions from the captured images. In our texture mapping work, we reproduce the appearance of the object by reconstructing the mesh and a texture map. Such a texture map encodes the lighting conditions where the object is scanned. To make the reconstruction relightable, one easy way is to recover the material properties of the object, which is usually represented by the BRDF. Many methods have been developed for spatial varying BRDF acquisition. Most of them require complex acquisition setups such as high-end street scanners. More recently, NetMetal solved this problem by capturing images of the object from different viewpoints using mobile phones with flashlight. They use traditional multi-view stereo to reconstruct the geometry, and to achieve this, they capture hundreds of images, which is very time-consuming. Recently, learning-based methods have been used for solving multi-view stereo method for solving multi-view stereo from a sparse set of images. While these works can produce high-quality texture depth maps, they only output a set of point clouds instead of complete geometries such as triangle meshes. Learning-based methods have also been proposed to acquire SVBRDF from a sparse set of images. For example, Li et al. Trains a neural network to predict the SVBRDF of planar samples from a single image taken with a mobile phone and a flashlight. Gao et al. Extended this framework to predict SVBRDF of planar samples from an arbitrary number of images taken from different viewpoints. They achieve this by optimizing a latent representation of the SVBRDF using a captured image. However, their method is still limited to planar samples. Recently, Li et al. Further proposed a method to predict the SVBRDF of objects with arbitrary shape from a single image. They only predict rough depth from the input images and cannot reproduce the full geometry. In contrast, our method recovers the full geometry and SVBRDF from a sparse set of 6 images. Given the geometry and the reflectance of the object, we can visualize it from an arbitrary viewpoint and normal lighting conditions. Our input consists of 6 images. These 6 images are captured at a vertex and the center point of its 6 adjacent faces. Such a setup has a large baseline. The angle between the adjacent cameras is about 37 degrees. This makes it possible for us to image the entire object with a small set of cameras. It also provides enough overlaps between views so that we can exploit stereo information to infer the geometry. In addition, different from previous works that require captures and different view light combinations, we capture the images and collocated camera light. That is, the light is always at the same location with the camera. This also greatly simplifies the requirement for acquisition setups, making sparse mobile phone captures possible. Given the 6 images, we first estimate per view depth using a deep multi-view stereo network. We propose a novel method to aggregate appearance cues across multiple viewpoints and reconstruct the per view SVBRDFs. We use a network-based optimization to fuse per view estimates and reconstruct a consistent mesh with per-vertex BRDFs. Let's look at the depth prediction first. To predict the depth at the view, we'll plan plane sweep volume for depth prediction. To predict the depth at each depth level, to predict the depth at a view, we divide the view frustum into a set of predefined depth levels. At each depth level, we warp the input images to this view using homography-based warping. The images on the right shows the combination of the warped images at the selected view. We can see that although the images are not aligned, although overall the images are not aligned, the combined images, the region indicated by the arrow are somewhat consistent. These regions are where the current depth levels are close to the correct depth of that part. If we do the warping for all depth levels, we can see that different parts of the scene are aligned at different planes according to their actual depths. Therefore, the sweeping volumes give us good cues on where the correct depth is across all the depth planes. Specifically, given 6 input images, we first extract a set of features for each input view. And then we build a 3D sweeping volume at the reference view by warping the feature maps of all views to a reference view using a prefixed set of depth levels. Then the 3D sweeping volume is fed to a depth network to predict the probability of each depth level, and we sum up the depth level according to that depth probability to get the depth predictions. While the network is able to predict reasonable depths, it suffers from inaccuracies in regions that are textureless and highly specular. To further improve the result, we use the guidance network to predict the guidance map from the reference image. Finally, we filter the initial depth with the guidance map with the guided filter and get the final depth. Now we have the depth at each of the input views. However, such depth is not able to represent the full geometry of the scene, and what we ultimately want is a triangle mesh with the per-vertex BRDFs. We propose to first estimate the BRDF and the normal at each of the input views. We would like to combine multi-view information for the prediction, since the multi-view information gives us cues about how a point looks like and different view-light configurations. Let's look at one of the input view as an example. Trivially, we can warp the other views to the reference view using predicted depths, and stack all the images together and feed them to an encoder-decoder network with script connections. This is the common network architecture used in previous SVBRDF acquisition methods. However, such a network is not robust to occlusions between views. Directly using depths to mask out occluded regions is also not feasible due to potential inaccuracies in depths. Therefore, a naive unit produces results with serious artifacts, as we can see from the right images. As we can see that there are significant artifacts in the albedo and the normal. Instead of stacking all the warped images together, we form the reference image and the warped images as pairs. And we feed each pair to an encoder network. This is done for all the input views, and therefore, for each input view, we get some intermediate features. Note that here, all the encoders share the same weight. Then these intermediate features go through a max pooling to get a common feature representation that encodes multi-view information. We feed the feature after max pooling to a decoder network to predict the BRDF and normal at the reference view. In practice, we also include the depth information at the reference view and the input view, as well as the lighting information. The usage of the max pooling can effectively mitigate the misalignments and occlusions between reference view and the other input views. As we can see from the result, it produces results with much higher quality. All the networks are trained on a large-scale dataset that contains 20,000 shapes procedurally generated from a set of basic shapes. Each object is textured using realistic materials from Adobe stock dataset. We render images using our acquisition set and our acquisition setup using a physically based renderer. With the depth network and the BRDF prediction networks, now for each input view, we have its depth, normal, as well as BRDF components. We build an oriented point cloud from the depth and normal maps and perform a Poisson reconstruction to reconstruct the geometry. To recover per-vertex BRDF, one naive way is to weighted blending the predictions at each view. However, in practice, it is inevitable that there exist potential inaccuracies in predictions and inconsistency between different views. Our SVBRDF predictions are computed from a single feed-forward network parse and are not guaranteed to reproduce the captured input images exactly, because the network has been trained to minimize the reconstruction loss on the entire training set and not this specific input sample. Therefore, simple blending the BRDFs at each view will result in blurry results, as we can see in the video. You can see that in the characters, the textures are blurry. We further propose to optimize per-vertex BRDF by minimizing the difference between the rendering image and the input images. Let's take albedo as an example. For vertex on the geometry, we get its BRDF at each view. And then its final albedo is the weighted sum of the albedo from each view. Similarly, we get its BRDF of other components such as normal, roughness, and specular albedo. And then that is given these components, we can get its rendered colors. And given the input images, we can also get the ground truth colors of that vertex from the input images. We minimize the difference between the rendered colors and the ground truth colors. This is done for all vertex and all views. By minimizing such a loss, we are trying to match our rendered images to the ground truth capture so that we can mitigate potential errors in the predictions. During optimization, ideally, we could optimize the weight and optimize the weight of each vertex and the BRDF at each view. Because of the sparse observations, independently optimizing the BRDFs leads to artifacts such as outliers and spatial discontinuities. Instead, we make use of our learned prayers to regularize this optimization. As mentioned above, the BRDF at each view is predicted with the decoder network from a common feature representation. During optimization, instead of direct optimization BRDF, we fix the weight of the decoder and optimize the feature representation for each view. These latent features, by virtue of this training process, capture the manifold of the object reflectance and generate a spatially coherent per-view SVBRDFs when passed through this decoder. Hence, therefore, optimizing in this feature space allowed us to adapt the reconstruction to the input images, and at the same time, leveraging the prayers learned by our multi-view SVBRDF estimation networks. This video shows the comparison between different optimization schemes. So without optimization, the rendering results are blurry, such as the video on the left shows. Directly optimizing the BRDF at each view results in discontinuities and outliers. In comparison, our network-based optimization can achieve results with much fewer artifacts. We compare against the previous classical inverse rendering method based on optimization. Our results can better reproduce the appearance of the captured object with much fewer artifacts. Also note that this previous method by Nam et al. Cannot reconstruct geometry, that they reconstruct geometry with multi-view stereo, and in fact, they cannot reconstruct the geometry with only 6 images. So they get their results based on the estimated geometry from with our method. This video shows another comparison on a highly specular object. This previous method failed to recover the specularities on the object, and at the same time, our method can better handle such a challenging scene. Here shows more renderings with our reconstructions and event map lightings. So far, we have talked about using match representations for appearance acquisition. Triangle matches are the most common way to represent the scene geometry in computer graphics and computer vision. However, When there are thin structures and textured regions, it's usually very challenging to recover accurate geometries, accurate triangle meshes directly from the captured images. Therefore, in our latest work, we apply volumetric representations to reproduce the appearance of real-world objects and scenes. Volumetric representations have been widely adopted in recent works. These methods are limited to pure view synthesis and fixed lighting conditions and do not support relighting. In contrast, in our work, in addition to learning a volumetric representation for the scene, we also jointly recover the geometry properties. We also jointly recover the material properties of the volume. Such a novel representation allowed us to visualize the object and arbitrary novel viewpoints and lightings. We apply a practical acquisition setup for this task, where we use the consumer mobile phone to capture multi-view images of the scene and flashlight. At the heart of our approach is a physical-based volume representation that captures scene geometry and appearance. Each voxel in the volume consists of opacity, normal, and reflectance. We apply differentiable remarking framework to render images and arbitrary viewpoint and lighting. During rendering, we trace the array toward each pixel and accumulate colors along array. For each sampling point along array, we calculate color using its reflectance and lighting information. To calculate the color of a pixel on the image, we perform a differential remarking along the camera array corresponding to that pixel. Given the position of the previous point, we determine the position of the next point of the next sample point by taking a step with fixed step size along the camera array. To calculate the color at a point, we need to know how much light will reach that point after absorption along array. Therefore, we perform another remarking from the lighting position. To account for the absorption in this process, we record the cumulative opacity at each of the sample points. We calculate using classical opacity compositing, where the first term is the cumulative opacity of the previous point, and the second term is the contribution of the current point. Similarly, we need to know how much of the reflected light will be absorbed along the camera array. Therefore, we also calculate the opacity at each of the sample points on the camera array in the same manner. Note that during training, since we train on images captured and collocated camera light, the light ray and the camera ray would be identical. So only a single pass remarking is needed during training. We use the parametric reflectance function to model how light is reflected at each sample point. For each sample point, the reflectance function takes in the view direction, lighting direction, normal, as well as the reflectance, including diffuse albedo and specular roughness as input, and returns the outgoing radiance along the view direction. It is further multiplied by the light intensity to get a final outgoing radiance. Then the final contribution of this point can be calculated by considering the absorption and scattering along both the camera ray and light ray. Here, the first term accounts for the absorption of the reflected light along the camera ray. And the second term accounts for the absorption of the incident light along the light ray. And the third term measures how much light is scattered at that point. These terms are combined to give the final contribution of the kind of point. And we accumulate the contributions of all sample points to get the final color of that pixel. We apply deep prayer-based optimization to estimate such a volume. We start from a 512 channel encoding vector, randomly initialized with a Gaussian distribution, and decode it into a 3D volume that has a size of 128. We use a 3D convolution neural network as a decoder. Each voxel in the volume consists of 8 channels, including 1 channel opacity, 3 channel normal, 3 channel diffuse albedo, and 1 channel specular roughness. As mentioned previously, we train the networks on images captured and collocated camera light. In this case, the camera ray and light ray at each point would be identical. Therefore, a single pass of rematching is needed to get the color of that ray. While we train the networks on collocated images, the learned deep reflectance volume can generalize to arbitrary novel viewpoint and lighting due to the utility of the physically based reflectance function. We use our loss function consists of 3 terms. The first term is an image reconstruction loss, which minimizes the L2 difference between the predicted pixel colors and the ground truth pixel colors. And the second term is the regularization of cumulative opacity along camera ray. It encourages the cumulative opacity to be either 0 and 1. That is, most camera ray should either hit the background or hit the opaque object. That is, when the camera ray hits the background, its cumulative opacity will be 0. And when it hits the opaque object, its cumulative opacity will be 1. Such a term helps to recover clean background without the need of background maskers for training images. It also helps get rid of the float artifacts in the empty space outside the objects. Finally, the last term is the opacity sparsity loss that encourages the opacity to be spatially sparse, and it helps to recover sharp boundaries of the objects. We compare to a state-of-the-art method that applies multi-view stereo for geometry reconstruction and estimate per-vertex BRDFs. We first compare on a scene with large areas of tactilized regions. Multi-view stereo failed to reconstruct the accurate geometries for tactilized objects and result in significant distortions. Our deep reflectance volume avoids these issues and models the scene geometry accurately. Our deep reflectance volumes also generalize to uncollocated camera light and produces the specularities and shadows accurately. Here shows a comparison on another real-world scene. The captured object here has complex geometries with scene structures such as the leaves on the tree. Mesh-based method fail to reconstruct these detailed structures. In comparison, our method is able to reconstruct the more accurate geometries and generate higher quality renderings. Our deep reflect volumes are also able to handle scenes with multiple objects. Our method can model complex occlusion between them and reproduce realistic cast shadows and novel lightings. Note that these cast shadows are never observed by our network during training. We also compare our renderings to ground truth images on synthetic data. From a comparison, we can see that our results match the ground truth very well. Particularly for images captured under non-collocated camera light, which are never observed in the training, our method is also able to generalize and produce shadows and specularities that match the ground truth closely. By combining the renderings of the objects and each single lighting corresponding to the individual pixels of the environment map, our method supports environment map renderings. Here we show a comparison between our environment map renderings and the ground truth. Inspired by recent works that learn continuous scene representation using neural networks. In follow-up work, instead of predicting a discretized volume, we learn an MLP to implicitly model the geometry and appearance of the scene. Given an arbitrary point in 3D, the MLP allows us to predict its volume density, normal, and reflectance. In addition, instead of using opacity compositing that only supports fixed step size, we apply physically accurate volume rendering based on the estimated volume density. Such a formulation enables us to perform remarking with different step sizes and allows us to do adaptive sampling in 3D space. Here we show a comparison between our results with the between our results with the discretized volume and a continuous MLP representation. From the result, we can see that our MLP representation can more accurately recover the details on the textures and the geometry structures, such as the leaves in a tree. This video shows some more results. Our method, so these two scenes has complex normal variations and texture details on the surface. Our method is able to recover these tiny structures and reproducing the appearance of these objects faithfully. Different from most of the previous new rendering works that require custom rendering module, and that is not consistent with traditional rendering engines. An advantage of our representation is that our learned representation is physically accurate, and it can be easily integrated with the traditional physical-based renderer. So in these two images, we show examples of combining our new representation with the traditional synthetic scene. Here, that is the left that is a cottage scene is a new representation learned with our method. And the teapot is a traditional synthetic scene represented by a triangle mesh and a BRDF. We rendered the composite scene using a physically based renderer Mitsuba and complex environment map lightings and area lightings. By doing so, we are able to simulate the light transport between these different representations, including complex interreflections, such as the interreflection between the object and the floor, as well as the interaction between our new representation and the teapot, as we can see here. So that's all for the introduction to some of my previous works. My vision is that in the future, when people take out their phones or other consumer devices, they can easily scan and reconstruct the 3D scenes in front of them. Instead of 2D photos, the future media for showing life experiences and memories would be 3D. I believe that efficient and accurate method for 3D content creation is the key to really make a thriving future for virtual reality and augmented reality. Many future works remain to be explored to make such a vision into reality. The first thing I want to discuss is sparse geometry and BRDF acquisition. Our SVBRDF work have tried to reconstruct full geometry and the BRDF from 6 structured images. To really make appearance acquisition more practical, we should be able to do it with a smaller set of images that are taken casually and mildly controlled or even uncontrolled lighting conditions. The combination of learning-based multi-view stereo and the learning-based sun-distance representation would allow us to reconstruct the high-quality geometry from a sparse set of images or rough depth maps from depth sensors on mobile phones. A combination of such method with learning-based BRDF estimation would be a potential path for more practical appearance acquisition. In addition, the appearance of learning-based method with the physical-based differentiable rendering would also be a future interesting direction. It would allow us to refine the initial predictions from the networks. In addition to traditional geometry and material representations, it is also desirable to explore novel new representations for scenes and objects. Specifically, it will be interesting to study how to efficiently reconstruct the new representations for complex real scenes from sparse captures. By reconstructing 3D scene and estimating its spatial wiring lightings and render photorealistic interactions between the environment map and the objects, we can achieve much better AR and VR experiences, especially for telepresence. Another research direction would be generalizable neural representations. While the recent development of neural representations have significantly improved the quality of the reconstruction, such methods need to be trained specifically for each scene. Researching into methods and representations that can efficiently generalize to unseen objects and scenes would be highly desirable. I'm also interested in investigating how to integrate the learned new representations with classical rendering pipelines. Currently, new representations need specific decoder for renderings, while traditional mesh and material representations are rendered with rasterizers or physically based path tracers. It is desirable to develop a unified rendering framework so that we can jointly render these two different representations. Each representation has its own advantages. By integrating them, we can selectively choose proper representations for different scene components based on their properties. This will make the process of 3D content creation more flexible. In the end, I would like to thank my advisor, Professor Rosa Momosi, and many other wonderful collaborators. That's all for my presentation. Thank you for listening.